Ah, yes, primitive man. The history of mathematics begins during a time when life was a bit more simple, but definitely not less challenging. All of the attention of early humans was focused on survival, which is where mathematics would first find its place within the human mind, and subsequently within the love chamber of the human heart. Evidence of counting dates as far back as 30,000 years ago with the Lobambo bone. As seen here, the Lobambo bone was discovered to have deep notches carved into it, which look like modern-day tallies, evidencing the earliest form of basic arithmetic and counting. Undoubtedly, this ability to count would serve as a useful tool for human survival. Another bone, called the Ishango bone, is estimated to be 24,000 years old and has the same feature of carvings that present as tallies, giving additional evidence of the counting hypothesis. However, while this is likely the first tangible evidence of mathematics, it is also possible and been argued and asserted that the notches were just for gripping the tool, not counting. What is now modern-day Iraq, Iran, Syria, Turkey, or collectively referred to as the Middle East or Western Asia, was once occupied by the Assyrians and Babylonians in the marsh fields of Mesopotamia. They traveled by canoe, lived in reed houses, and gave us the first documented record of mathematics. We credit this nascent society with the first positional notation system that relied on a sexagesimal system or base 60. This just means they operated with 60 digits, while we use 10 digits, 0 to 9. There are trade-offs with different base systems, but one is not superior to the other. One major impediment, however, was they did not have a number 0, so there was much ambiguity in the notation that could only be resolved through contextualization. Without the 0 placeholder, any string of digits could have any infinite number of values that could only be deciphered by understanding the context or the application the numbers relate to. Fortunate for modern-day historians, Mesopotamia used clay tablets to document their mathematics, perhaps the most durable form of documentation humans possess. Preserved to this day, there is a Babylonian tablet stored at Yale University, collection number item 7289. The clay tablet attempts to calculate the square root of 2, arriving within 0.000008 of the correct answer, which, by any stretch of the imagination, is remarkable. They even attempted to solve quadratic equations with their inconsistent and many times incomprehensible language. Of course, they did not use alphabetical symbols or the familiar notation we have today because, well, the alphabet was not even invented yet, and they did not document any general formulations or theorems. In other words, they had tables of figures and specific case problems, but no mathematical theorems. It is possible they unknowingly used theorems like the binomial theorem, the Pythagorean theorem, or other geometric proofs to solve individual problems, but they clearly did not identify these universal principles involved in their calculations, or put another way, they did not prove their solutions. Despite all of that, however, Mesopotamia was the first to take one step towards mathematics and to make one giant leap for mankind. Unlike Mesopotamia, ancient Egypt documented their math on papyrus, paper-like material from a papyrus plant, which, as you might imagine, is much more perishable than clay tablets. This means little has survived from ancient Egypt, but evidence of mathematical thinking does exist even with such few direct records. But this forces you to think, should we be concerned that our modern-day knowledge may one day be lost? Are there steps in place to prevent this? We now join the ancient Greeks in the golden age of mathematics, which should have undoubtedly impressed and pleased the gods. Ancient Greece and their polytheistic tradition of many gods had been vibrant for millennia, but it wasn't until around 600 BC did they begin to make a foothold in mathematics. The first major figures in mathematics were Pythagoras of Samos and Thales of Ionia, both of whose contributions may have been embellished. For one, Pythagoras is synonymous with the Pythagorean theorem, but there is evidence that Mesopotamia used it well before the birth of Pythagoras. There is no direct evidence from this time period of the contributions made from Pythagoras or Thales themselves as individual human beings. It is all a second-hand account that was written down many centuries later. For example, the earliest written record of the mathematical contributions of Thales came from Proclus Lysias, a Greek philosopher nearly 1,000 years after his death. In fact, there is virtually no surviving records of mathematics or science from ancient Greece until we reach the time of Plato. That being said, the Pythagoreans and the Pythagorean school did construct mathematical concepts with general theorems, giving us structure for the first time rather than simply performing arithmetic on a given problem. They were the first people to believe that the operations of nature could be understood through mathematics and deliver on that belief. Thales and Pythagoras were the first real mathematicians in this sense. They gave order to mathematical ideas so that the knowledge could be propagated to and built upon by future generations. The Babylonians operated more on a case-by-case basis, trying to solve problems, while the Pythagorean school synthesized what we now call geometry, and they furnished the beginnings of number theory. It is now the end of the 5th century, and Socrates has been executed. Socrates, while an incredibly influential historical figure, did not make any contribution to mathematics, and in fact may have been a net negative on its development. So let us recognize a pair of people whose influence usurped even that of Socrates: Plato and Aristotle. Unlike Socrates, Plato cherished and embraced the power of mathematics, making it a core component of the curriculum at the Platonic Academy of Athens, the mathematical center of the world during that time. While Plato himself did not discover any new theorems, he is credited with fostering an environment that incentivized progress in pure mathematics, the outcome of which resulted in many discoveries. Aristotle, for all his praise, really did not make any tangible contribution to mathematics, but his approach to thinking may have influenced future mathematicians, especially where infinity is concerned. Let's meet Eudoxus of Cnidus, a Plato pupil whose mathematical theorem regarding ratios and proportions was so important it was documented in Book 5 of Euclid's Elements, a text we will learn about shortly. The definition Eudoxus wrote in English says,
"Magnitudes are said to be in the same ratio, the first to the second and the third to the fourth, when, if any equimultiples whatever be taken of the first and third, and any equimultiples whatever of the second and fourth, the former equimultiples alike exceed, are alike equal to, or alike fall short of, the latter equimultiples respectively taken in corresponding order."
Now, if you are like me and reading this makes literally no sense, then it underscores just how valuable mathematical notation is for understanding complex ideas. If math wasn't difficult enough, imagine working with this rhetorical language, like the one we just quoted now. Before I jump into the proof though, Eudoxus's definition is the precursor for using what we now call cross-multiplication to find a common denominator, and then we can confirm whether or not two fractions are in fact equivalent, or we could also add and subtract them. But let's return to Eudoxus's proof and represent it with a modern mathematical presentation. Let's say we have four different quantities, A, B, C, and D. Now, let's create a relationship where a ratio is formed between the quantities A and B, and between the quantities C and D. Alright, so this should look familiar enough. We have two fractions. Now let's try to set these fractions, or ratio of integers, equal to one another. But they can only be equal to one another if and only if given two arbitrary integers m and n that one of the three following conditions are met. The first condition would be the product of ma is less than the product of nb, which implies that the product of mc is less than the product of nd. Now the other two conditions would be exactly the same, except we switched the sign. So instead of less than, we have greater than, and instead of greater than, we could have equal to. Now this might still be a bit confusing to look at as well, so here is a modern day example to try and help clarify all of this. Let's set our A, B, C, and D equal to some quantity. A is equal to 1, B is equal to 4, C is equal to 72, and D is equal to 288. So we have a fraction of 1 over 4 equal to 72 over 288. And that is only true if and only if conditions 1, 2, or 3 are satisfied. Also, we could say and if we use different sets of m and n. So if we set the integer m equal to 2 and the integer n to equal to 4, we get that 2 times 1 is less than 4 times 4, which implies that 2 times 72 should be less than 4 times 288, and that in fact does check out. Now we could set m equal to 20 and n equal to 2, and we discover that 20 times 1 is greater than 2 times 4, which implies that 20 times 72 should be greater than 2 times 288, which is in fact the case. And then lastly, we could set m equal to 4 and n equal to 1, such that 4 times 1 is equal to 1 times 4, which implies that 4 times 72 should be equal to 1 times 288, and that in fact does check out. So our A to B ratio is equal to C to D ratio, given that our conditions were met. It highlights how impressive we were thousands of years ago, and it foreshadows how impressive we still can be. A pupil of Eudoxus, Menaechmus, is responsible for the first description of conic sections, commonly referred to today as parabolas and hyperbolas. Among the chief authorities attributing conic sections to Menaechmus was in a letter from Eratosthenes to King Ptolemy Euergetes quoted 700 years later by Eudoxus. Following the death of Alexander the Great, the lands in Egypt were firmly in the control of Ptolemy I, who established a school of scholarship called the Museum. It is here where the most influential mathematical text ever composed, Euclid's Elements, was written. The Elements is a 13-book accumulation of mathematical knowledge in geometry, algebra, and number theory up to that time period. Interestingly, in Book 9, there is evidence of the first elementary proof that the number of primes is infinite, Proposition 20. A fragment from the original text was discovered during the 1900s in a group of manuscripts called the Oxyrhynchus papyri. Only 1 to 2% of the contents at this ancient site have been analyzed and deciphered since the early 1900s. It is no surprise that most of the mathematical success up to that point rested in geometrical proofs given their real-life application, but we can see theorems in other areas were beginning to be discovered. Euclid's Elements have been copied and passed down for millennia, with few revisions, boasting at least 1,000 editions. Only the Bible and other religious texts can claim so many editions, making it one of the most influential texts of any category, not just mathematics. Perhaps the title of single greatest mathematician of antiquity can go to Archimedes of Syracuse. Briefly studying at Alexandria under the students of Euclid, Archimedes would go on to be the first true physicist. Unlike Aristotle, whose approach was speculative and non-mathematical, Archimedes described the mechanical relationships of objects from simple postulates in his work on the equilibrium of planes. Archimedes would follow this up with a work called On Floating Bodies, where he made the discovery of buoyancy. The book contains much more than buoyancy, evidencing his uncanny mathematical ability. This ability could have warranted him a faculty seat even today where he could teach pure mathematics. Perhaps his greatest work, On Spirals, Archimedes unknowingly constructed a primitive form of calculus, stumbling upon the idea of a line tangent to a curve, what we now call the derivative, preceding even the great Sir Isaac Newton with an antiquated form of differential calculus. Interestingly, of all the writings by Archimedes, this work was largely ignored because of the difficulty to grasp the concepts. The ancient Greek appetite for geometry, algebra, and number theory from a theoretical perspective was robust and began a revolution that would become known as mathematics. They showed a proclivity to thinking in general terms about numbers and their operations beyond just applications and problems, like that of the Babylonians and Egyptians. The Greeks even relegated routine computations and calculations to their slaves. That being said, the mathematicians of this time period were also astronomers, working to describe the universe with their newfound mathematics. In fact, Apollonius of Perga, another great mathematician of ancient Greece, proved additional theorems regarding conic sections just in an effort to describe planetary motion. Astronomy would motivate the ancient Greeks to create a more systematic approach to angles and chords, building off the work of other geometers of the previous centuries, synthesizing the beginnings of a branch in mathematics we now call trigonometry, whose development would be influenced greatly by ancient India. But every great civilization does come to an end.